Hi, my name is Jim, and this is part 2 of our filters lecture, and we're going to be working with second order low pass LC filters, and then we'll move into second order op amp based circuits. And this is a very good way to start. LC circuits are used in RF, and they have certain advantages even at lower frequencies. The L is the issue with regard to the size and cost. Usually it's cheaper to do it with op amp and couple resistors and capacitors. But this will give us a relatively general introduction to some new materials, and it's going to seem kind of strange as we move into this, but it'll be very useful when we actually get into the second order filters. So a second order filter has two energy storage elements. In this case it's an L and a C. And a claim to fame on that is it can give a roll-off rate of -40 dB per decade compared to -20 dB per decade for a single order filter. So what that would look like is if we have a second order filter, that would be, say, -40 dB per decade. With a first order filter it would be -20 dB per decade. So we can get a better roll-off rate. And in some circuits that's very important. For example, the anti-aliasing filter on anything that's sampling the signal, with the exception of software-defined radios. Further, what we can do for high-pass filters is would give us a +40 dB roll-up as opposed to a +20 dB roll-up for a single order filter, sometimes called a single time constant filter. So, I'm going to be talking here about F sub 0 instead of F critical, and they mean the same thing. It's just that this is a common language that's used when we're working in what we're going to be calling the S plane coming up. And we also need to be very careful and comfortable with the quality factor Q. And this is kind of from the same form as a series resonance circuit. And if we take a look at a series resonance circuit here, like this is, it's also a filter. What's the difference? Depends on Q. So if Q is very high, we get a very peaked response, and F sub 0 is very high here, and that would determine the bandwidth of the circuit, which is the distance between a -3 dB point on the low side and a -3 dB point on the high side. Now if we increase this resistance, the Q is going to drop. And we can actually reach a point where it's relatively flat out to the critical frequency and then picks up a roll-off of -40 dB per decade. So from this you can see that the Q is a very important thing in determining how a filter is going to work. So Q is defined as, for our case here, but basically there's three definitions. It's equal to the absolute value of X over R, and the absolute value simply means that we're not concerning ourselves with the angle, only the magnitude. And this will be for any component in L or C. In a series resonance circuit, that's what we would be using, X over R to find the Q. And in a parallel resonance circuit, Q is defined as R over the absolute value of X. Now why the difference? Well, in a series resonance circuit, the R is in series with the circuit and would tend to absorb energy. We're in a parallel resonance circuit, R is in parallel with L and C. So the higher the R is, the lower the amount of energy that's going to be absorbed. So for a high Q circuit in a parallel tuned circuit, it would be good for the R to X ratio to be very high. Once again, another definition for Q is equal to the bandwidth divided by the resonant frequency, where the bandwidth would be defined as the distance between the 70.7 points relative to the peak or the -3 dB points, same thing. So let's take a look at our circuit here and have kind of a high Q in it, and instead of giving us a response that's flat, it'll actually be a response which has a roll-up in it, and this is called peaking. And that would kind of look like this if we were to, say, sweep the circuit. So we get a little peak out at the end, and that can become kind of severe. And if we elect to shock excite the circuit, which has a Q which is kind of high, is what we'd see is on the edge of a rectangular pulse is we would get a ringing component. Now, this is called the transient response, and it derives itself from the mathematical term called a delta function, which is a pulse of infinite amplitude and zero area. We're emulating that with the sharp rise and fall times of a rectangular pulse, and then the circuit will oscillate in a damped way here because it's dying out at its natural frequency. So by shock exciting this, we can kind of get an idea of the way it's going to behave. Now, say we have a low pass circuit, do we need to worry about that shock exciting stuff? Well, I don't know, think about a drum beat, striking a cymbal. Yeah, we need to worry about it, because this, in an audio system, is going to produce artifacts that perhaps we don't want to listen to. So there's a little bit more to this. Obviously, we have the frequency response, and then we have the transient response, which can add, I don't want to call it distortion, but anomalies in the signal response after going through the distorted network. And we're only concentrating here on low pass. High pass are similar, but there's only so much time, and it's it's good enough just to do low pass. So we have a new tool available to us, and that's going to be the Laplace transform. And what that's going to allow us to do is to take our linear arrangements that we're used to working with and transform it into the S domain. And S is referred to as a complex variable. Now, to do that, we have our circuit parameters here, and we do a transform on it into the S domain. We operate algebraically on the circuit, figure out what we need to figure out, and then do an inverse transform and get it back into our starting domain with a solution. Now, the claim to fame of Laplace transformations, is that in calculus we have integration and differentiation, and in some of our circuits that can really kind of get mathematically complicated. Once we're in the S domain, we can simply manipulate, that is, do differentiation and integration by algebra, and that's certainly simpler. Now, you're kind of familiar with changing domains. You've done it many times, and that would be from the linear domain into the log domain. Do the operations in the log domain, transfer it back into the linear domain. And the advantages of the log domain is that multiplication in the linear domain is adding in the log domain. Division in the linear domain is subtraction in the log domain. Exponentiation in the linear domain is multiplication in the log domain. And finally, taking the root in the linear domain is the same as dividing in the log domain. Now, what I purport here is that working in the log domain involves simpler operations on our system than in the linear domain. And the overhead on this is to do the initial transform into the log domain, doing the work, and transform out of it. But it's the same thing with the S-plane. And there's tremendous advantage in using algebraic manipulations instead of using derivatives and integrals. So we take a look at the S domain as we have the complex variable S, and we can define it in two ways. First is by the symbol sigma, and that's going to be the real part of the transform. And then the imaginary part is what we're used to seeing is the j omega. And if we take a plot of the S domain, what we see, it would look like this, with positive sigma, negative sigma, positive j omega, negative j omega. Further, we can define the S as replacing j omega. So we're going to be working with both of these definitions of S here. Now, where we want to be in the S plane for filters is in the left-hand side of it. And I kind of dotted this because this is the side that's stable. Now, If you're operating here and you're not on the j omega axis, the circuit cannot oscillate. Now with our LC filter, it can't oscillate anyway because the only energy into the circuit is the signal. We don't have external power, and the Barkhausen criteria states that to have an oscillator you have to have a power input. So because an LC filter has resistance, say in the coil windings, and maybe in addition what we want to add is we can never get to the j omega axis. So it's quite not possible for an LC filter to oscillate. We just don't have the energy to do it. But as I showed on the previous page, is we could cause an awful lot of peaking, which may or may not be desirable depending upon what we want to do. Now the right hand side of this, where we're dealing with a positive sigma here, we will get oscillations up in this area without question, and we'll get a rising exponential over on this side without question. So for filters, we kind of want to stay away from the right hand quadrants 1 and 4 of the S. Poles and zeros, some more new stuff. Filter in the S-plane has a transform that involves what's called poles and zeros. Now, zero is pretty easy to understand. It's the point in the circuit where basically the signal will not pass through it. There's zero output from the signal. And in a low-pass filter, for example, as our frequency goes to infinity, our output voltage will go to zero. And we can kind of see that curtailing here. And if we let F go to infinity and just get lower and lower and so forth, it would approach, V out would approach 0 volts. So what we would say is we have a 0 at F goes to infinity, a 0 transmission point. Now, let's look at a high-pass filter. Well, in this particular case, as we go lower and lower towards 0 hertz, we're going to pick up a 0 transmission point. So in this case, we would say we have a 0 at 0 hertz. Now this is a finite 0. Low pass is an infinite 0. So the way we would specify that 0 on the S-plane for a high-pass filter is at the origin of the S-plane we would put an O there. And that would tell us where the 0 is. Okay, so if for a pole it'll be an X, and we'll get into that in a minute. Okay, poles. Poles relate to the critical frequency and is designated by an X on the S-plane. And a second order filter can have several different pole locations. So stay tuned here. I know all this is new. So pole configurations, and if we have a quality factor less than 0.5, and remember that's going to be the ratio of R to X, what we say is the circuit is overdamped. And that means that we're going to get a lazy roll-off point. So let's talk about damping for a minute. Suppose I have a clock and a pendulum's hanging down and I take it and I release it. Well, the pendulum's going to swing back and forth and cut a sine wave through time, and because of friction and losses, the amount of swing is going to decrease and eventually be 0. Now if I take that same pendulum and put it in water and draw it back the same distance and let it go, it's going to oscillate maybe once, twice back and stop. I have damped the pendulum with water. So in a damped circuit, we're damping it with resistance. Same thought. So if we have Q, quality factor less than 0.5, we still get our negative 40 dB per decade roll-off eventually. We have a lazy corner here. And if we were to locate poles on this, is what we would see is we have 2 real poles on the negative real axis designated by negative sigma. So if we take a look at the denominator of our transfer equation, which we'll be seeing in a minute, for a second order filter it'll be a quadratic equation. Kind of makes sense. And we would solve that by the quadratic formula. So if we have this situation of being overdamped, the value under the radical is positive. and that's why we get two real poles on the negative sigma axis. Now we're going to go through all three permutations on this: positive, 0, and negative. So let's take another look at this, and in this case Q is going to be equal to 0.5, and that's referred to as critically damped. Now if we again solve this, is what we would see is the area under the radical is going to be 0. Therefore we have one pole, because it's plus or minus 0, located on the negative real axis. What we see in the response here is that it's not quite as lazy as it was before, and it achieves an ultimate roll-off of negative 40 dB, as will any second-order lower high-pass filter. Okay, one more case. Okay, we have two poles, and this is going to occur when our Q is greater than 0.5, and this is said to be that the circuit is overdamped. So 0.5 is kind of the borderline between underdamped and overdamped. And if we were to take a look at the response here, is what we would see would be a peak out by the critical frequency, and then it would achieve its negative 40 dB per decade roll-off. Now if it's overdamped, what happens is under the radical becomes negative. Well, that's nice. So how do we take the square root of a negative number? And the answer to that is we take the square root of the positive number, we treat it as positive, and then we place a negative j in front of it. So what this would look like would be negative j times the radical, and we would end up, for an example, of negative 1k, that would be this guy, plus or minus j 500. So we cannot take the square root of a negative number, but if we use j to represent that, after we treat it as a positive number, all works out well. So this circuit's overdamped, and if we were to hit this with an impulse, we would see the ringing as before. In the case of the critically damped and the underdamped, there would be no ringing. A rectangular pulse would come up, kind of round itself off a little bit, and then achieve stability at the top and the bottom, where the slope is approximately 0. So in summary here, in the S-plane, if we're on the left-hand side and we have poles that are on the negative real axis, we're going to have a response that looks like this: a decaying exponential represented by, in general form, e to the negative x. If we have a pair of poles, plus and minus j 500, these are said to be complex conjugates. Now, what that means is the real component is the same, but the imaginary component is the opposite sign. And they would locate here in quadrants 2 and 3. And depending upon how near they are to the j omega axis determines how much ringing we're going to get. So in your mind's eye, just think about this as being on a half circle here. If I take these two poles and slide them toward j omega, the ringing becomes larger. If I take the two poles and slide them back toward negative sigma, the ringing becomes less and less pronounced. And if I'm on negative sigma, the negative real axis, there is no ringing. So now looking at the right hand side, if we're in quadrant 1, is we're definitely unstable, and what we see is a sine wave starting at 0, say when we turn the power on, because this has to be a powered circuit, which will produce sine waves that rise in accord with e raised to the positive x. Eventually these will stabilize as it hits the power supply rails, because it can't get bigger forever. If we look down in quadrant number 4, is what we see is a rising exponential. Again, e to the positive x. So that kind of gives us an example of what goes on in the S-plane with regard to where we are located. Filters always need to be over here. Okay, let's take an example of a first order low pass, and then what we'll do is we'll introduce some new terms and then evolve that into a second order a little bit later. So this is going to be my circuit here in R and C, and for the sake of illustration, I've let R equal 1 kiloohms and C equal 100 nanofarads. And the mission here is to find F sub 0, omega sub 0, which is the radian frequency at the critical frequency, I guess the critical radian frequency, and we want to plot the poles and the zeros. So what's absolutely important to note here is that omega 0 is equal to 2 pi f0. And you can't flinch on that. I mean, you have to be very comfortable working with omega, because that's what a lot of stuff works with. So omega 0 is defined as the undamped natural frequency in filter speak. Likewise, f sub 0 would be the critical frequency, represented as frequency in hertz, would be equal to omega 0 divided by 2 pi. So we're going to be popping back and forth between these quite a bit, so you need to be comfortable with them. Now, the S-plane has different variables to use in it. We have to figure out what those are before we can use them. So let's start with the capacitor. We have capacitive reactance is equal to our guy, and we can also represent that as 1 over omega c. And if I wanted to represent that as the impedance of a capacitor, I would say that Z sub c is equal to negative j 1 over omega c. Now the difference with this, and the reason we don't have a negative j here, is that the word capacitive reactance, along with its attendant symbol x sub c, includes a magnitude and an angle. It's in the words, so we don't have to specify it with anything like this. Now if we want to substitute S for j omega, what we would do would take this and convert it into 1 over SC. Now in the S-plane, this is the guy we're going to be working with. Now let's do the same with inductors. They're not in our circuit, but we need to know what they're going to look like, because they will be soon. So x sub L is equal to 2 pi FL, which is also omega L. And the impedance of an inductor is j omega L. And if we want to move this into S-plane verbiage, we would represent j omega L by SL. So these are going to be the two forms that we're going to be using to represent capacitors and inductors respectively. Okay, solving the problem. Typically what we do, and we're given something like this, is we have an input and we want to find out what V out is going to be. So what we would do would be just set that up as a voltage divider, the impedance of the capacitor, divided by the total impedance, and multiply that by Vn. So that's all well and good. You should know how to do that from AC circuits. But now we're going to introduce something called a transfer function, which is designated by H. And what that is, it's the ratio of the output to the input. So it's pretty easy to get. All we have to do is take our guide here and divide both sides by Vn, and what we get is V out over Vn is equal to the equation that defines our circuit. Now, since we're operating in the time domain, I'm going to be using j omega here to illustrate that. And basically, we have an input voltage, a circuit, and an output voltage. And what does the circuit do to the signal? It does that to it. Okay? Note that both sides of this are dimensionless. We have volts over volts and ohms over ohms. So, in the S domain, what we want to do is replace j omega, or 2 pi f, with its S equivalent. So my ZC here is going to be represented by 1 over SC, and you can kind of see that relates nicely to 1 over 2 pi FC, or 1 over omega c. In the denominator, same thing, 1 over SC plus R. Now, in the manipulation of this, I have my transfer function, and note that this is in the S-plane, as opposed to the j omega. So this is kind of ugly. I mean, we've got fractions everywhere, so let's kind of clean it up a little bit. And we'll do that by multiplying by 1, numerator and denominator, by SC over 1 divided by SC over 1. And then, as you can see, that'll give us this form here, 1 divided by 1 plus SCR, or SRC, does not matter. And that'll be kind of the form that we're going to be working with. So this is an S-plane representation using the complex variable S of this circuit right here. So, let's just take a look at this now. Let's find a critical frequency, and we need to do some definitions before we can do that. So we'll let find a critical frequency, the magnitude of x sub c equal R. So 1 over 2 pi fc equals R. and then we'll solve for f. The frequency on this, f sub 0, which is the critical frequency, is 2 pi times the resistance times the capacitance. And if I elect to multiply this by 2 pi, what I'll do is I'll move 2 pi out of the denominator here and put it into the coefficient of f here, 2 pi f, and then I can represent this by omega 0, and therefore state that omega 0 equals 1 over the product of r times c. Contrarily, I can also say that rc is equal to 1 divided by omega 0. Now this is going to become very useful here because we want to get this in what's referred to as standard form, and that involves omega 0. So we're going to continue with this. This is the guy we had on the previous page, 1 over s CR. And kind of help us out here, seeing that we have this definition, we'll multiply numerator and denominator by 1 divided by RC, and that'll give us this step here, 1 over RC divided by 1 over RC plus S and S. And now, since we've defined this term right here, we can substitute in omega 0 divided by S plus omega 0, and that's kind of our standard form. So this is the guy that we wanted, and this is a low-pass response. So, in a roundabout way, we got here to do it, and you might say, okay, that's nice. What good is it? And, well, we'll see. It has values, you'll see. So, the numerator of this, omega 0, has a 0 at f equals infinity. And this is called a non-finite 0 because of infinity. So we've kind of answered that question. And when we're dealing with the S-plane, numerator and denominator, numerator is where the zeros are defined, and the denominator is where the poles are defined, which we'll be talking about here in a minute. So we know the numerator, and let's analyze the denominator. So what we want to do is solve for S, and the way to do that is set it equal to 0, and then manipulate this until we get S alone. And that's not hard to do. We'll just subtract omega 0 from both sides, and we find that S is equal to negative omega 0. Now that may seem kind of strange, but it works out. Or we could say that S equals negative 2 pi f sub 0 if we want, but we'll stick with omega 0. Then we'll use this substitution again and say that S is equal to negative 1 over RC. So we're getting there. Let's substitute in our values of R and C here. S is equal to 1 divided by our 1K resistor times our 100 nanofarad cap equals 1 over 100 e to the 6th, gives us negative 10K radians per second. So if we wanted to find out what the frequency would be, f sub 0, and note the units here, we would take negative 10K rads per second and divide it by 2 pi rads per cycle, that is, rads per unit circle. And in so doing, that would give us negative 1592 cycles per second, and that's the same as negative 1592 hertz. Now to plot this on the S-plane, we would put an X on a negative real axis here, and the reason is we don't have any complex values down here. We don't have a quadratic, so we don't have to worry about that. And that would locate at negative 10K rads per second on the negative sigma, the negative real axis. And this is absolutely stable. There could be no oscillations in this. The response would look like this. Only this would be negative 20 dB per decade because we haven't introduced our second energy storage element yet. Now we're going to take a little break here, and I'm going to take the camera and plant it in front of a computer and take a look at the S-plane. And when I work with this, grinding through the math is kind of straightforward, but what does it mean from the standpoint of really understanding it? And it wasn't until I saw a three-dimensional graph of the S-plane that I really understood what this means. And that's what we're going to do, is kind of look at this. where the membrane, yes, membrane if you will display the pole as an infinity going up at the critical frequency, and then the zeros as we move further and further away from the origin. So we'll see in a little bit.
This is a pole of a single order filter, also called a single time constant filter, and this is a J omega axis, and that in the lecture was drawn such that it was at the top and the negative J omega axis was at the bottom. The positive real axis sigma was to the right, and the negative real axis negative sigma was to the left. So basically this is a rotation where the real axis sigma is going across the diagram, and we're looking at the J omega axis. So basically this is going to be quadrant number 3 and quadrant number 2, and we're looking from the right hand plane into this. So what we see here is this strange shape, and the pole in this case is located on the real axis. We can't see it, but it's actually underneath the very peak here. So what's outlined in red is the frequency response of the curve. Now, where does this come from? And if you remember, when we solved for the denominator in the single time constant filter, we had S plus omega 0 equals 0, and found S to be equal to negative omega 0. So if we go back to the original on that, S plus omega 0, and if S is equal to negative omega 0, then as the actual frequency approaches positive omega 0, that is 2 pi f, we end up with a 0 in the denominator. So what we're seeing here at this point is the result of a divide by 0, and this line would extend up to positive infinity. So the S-plane is like a membrane, and if we take a knife and cut the J omega axis here, cut the membrane if you will, is where we start at J omega 0 right here. Going off to the upper part of this would be the actual frequency response of the filter. So what we can see here is we have a real zero, real pole rather, sitting at omega on the real axis, and it in fact is a low pass function. Now this stops here because we have an infinite 0 off the sheet. So in your mind's eye, when you're thinking about the S-plane, in the 3D projection of it, this is what it would look like, and all you have to do is slice this guy along the J omega axis and look into it. So we're looking into, in this point here, quadrant 2. That's the quadrant of interest. So that's how we get this shape here, is by the denominator having the complex variable s, which in this case was equal to negative 2 pi f, equal 0 as the frequency approaches positive 2 pi f. So if I were to take this 0 now, kind of looking forward, and move it in this direction and toward the camera, is what we can kind of see is that when this cuts this, if it wouldn't be in the middle here, and this were over to the right, is we could get some peaking out here where perhaps the shape would look like this and then drop off. So the location of the pole is going to determine the shape of the filter. Now this is absolutely tame because with a single time constant filter it can't do anything else but be tame. It can't have any peaking in it. So that's a good view, I think, of the S-plane and the pole location and how it actually works. And if you just think of this as kind of like I call it a membrane or a sheet, all you have to do in your mind's eye is cut it along the J omega axis and look into the second quadrant. Now coming up next for a short video clip is we're actually going to have 2 poles, and that'll be for the second order, and this pole will be closer to the J omega axis and not on the real axis, and that'll give us the ability to actually poke this up a little bit and we'll see a little bit of peaking. So that's what the S-plane looks like for a first order filter.
We'll continue with an example for a second order filter. And what we'll design is a maximally flat filter, which the industry calls a Butterworth, and that's defined by having a Q of 0.707. So there are names for certain filter types that have specific responses, especially in the world of operational amplifiers. So a Butterworth is very, very popular because of this maximally flat frequency response. Gets into the corner, it has a fairly nice corner, and the roll-off again is negative 40 dB per decade. So this is what our filter looks like as before, and our transfer function here, and what we'll use basically, before I get into that, is voltage divider. And in the numerator we have negative JX sub C, because that's where our voltage is formed across, and then in the denominator we have the total impedance, and our transfer function here is a function of J omega. So first thing we want to do is convert that into the S domain. So the transfer function in the S domain is substituting in 1 over SC as we did before for the capacitors, and SL for the inductors. We end up with this denominator here. And what we want to do is kind of clean this out a little bit. Again, we have fractions in the numerator and denominator, so we'll multiply by 1, SC over 1 divided by SC over 1, and that'll clear out the numerator, giving us 1. And then the denominator, as you can see, we have the squared term with an S and an S, and to arrange that into normal fashion here, we'll have the squared term first. So our transfer function in the S domain will be 1 divided by S squared L times C plus S times RC plus 1. Now it's desirable to get the S squared term all by itself, and we have an LC here, so what we want to do is factor that out. You kind of have to be careful when you do this. So here I've extracted the LC, and I'm going to be multiplying that by the rest of the terms inside the parentheses. So if I'm multiplying this by the S squared, as you can see, we end up what we started with. And then for the second term, I'm going to divide that by LC, so that when I multiply by LC, I end up with what I started with. So that's kind of a safety check to make sure when you're factoring this is that you don't make an error. And then in the third term here, which is 1, I divided that by LC, and once again, when LC is distributed across this term, that'll end up giving us 1. So there's no errors. So before we continue with this again, we have to do some relationships, so we can do some substituting coming up. And my critical frequency is equal to 1 over square root of LC, and then I can multiply both sides by 2 pi, giving 2 pi f sub 0 equals 1 over the square root of L sub C, of LC rather, and then substituting omega 0 for 2 pi f 0 gives us 1 over the square root of LC, and that's going to be the important relationship that we're going to be using to try to get this into standard form. Again, going back, we've got an L here that we're going to have to deal with, so it needs to be substituted with something, and we'll start out with letting Q equal the absolute value of X over R, as we did before, and then we'll end up with a final value here of omega L over R. So what I know then is that Q equals omega L over R, and I've just rewritten that here, and then I want to solve that in terms of L, so that at some point I may have to substitute this in for this L after we maybe move it around again. So this is going to be an important substitution, and so is this. So let's continue. So here's our transfer function, and what I want to point out before we go further here and kind of clear things up a little bit is that we have 2 C's, numerator and denominator, that are going to cancel, so I am not going to bring those down to here. Just wanted to let you know what happens to them, so I don't think they mysteriously disappeared. So I'm going to be multiplying both numerator and denominator by 1 over LC with full attention that I'm going to be substituting that later for omega 0. So in so doing, we end up with this form here, 1 over omega c in the numerator, s squared r over l, s, and then 1 over LC in the denominator. And what this LC did is it divided out this term. It doesn't mess with anything inside the parentheses because the LC is distributed across all of these. So it was divided out before the distribution, so we don't have to worry about anything inside except simplifying the middle term there by dividing out the C's. Now, next step, to try to get this in standard form, and I'm going to do this in 2 steps, is to take what we determined on the previous page, L equals Q over R times omega 0, and substitute that in here for L. So we have R over QR times omega 0. And next step is that I'm going to divide out the R's. And what that's going to give us here is omega 0 divided by Q. So in that substitution now, what we have here is a good form for the middle term. And when we go to solve this guy, that's going to become the coefficient b in our quadratic equation. Now, again, let's take a look at this other term here, 1 over LC, and see if we can clean that up a little bit. So what we can do with that is remembering that omega equals 1 over the square root of LC, and this is how we got it. F sub 0 is 1 over 2 pi square root of LC. Then multiplying both sides by 2 pi gives us 2 pi F sub 0. And then that turns into omega equals 1 over the square root of LC. And then what we'd like to do is get rid of the radical in the denominator. So we'll square both sides, giving us omega 0 equals 1 over LC. And you kind of can see from that what we're going to be doing up in here, if that is equal to omega 0 squared. So, coming back down into the denominator and doing that substitution, we end up with our transfer function. And this is just written down again. And then when we substitute in omega 0 squared for this, is we end up with our final product here, omega 0 over s squared, omega 0, keep forgetting the 0 there, over q times s plus omega 0 squared. So that's our standard form for a second order low-pass filter. Now, what we have to do with that is to get it into a different format down here. Now, an alternate form of the standard form, using what's called the damping ratio, and this is the Greek letter zeta. And what zeta is equal to, it's defined as, by the industry, is 1 over 2q, and contrarily, q is equal to 1 over 2 times zeta. And then if we do a substitution on this, we see the alternate standard form, and I just wanted you to see this. We're not going to use it because this pops up every now and again. Is that in the denominator it's s squared plus 2 times zeta times omega 0 s plus omega 0 squared. Okay, so let's design one now that we've got all the equations figured out. And this will be our second order guy. We want it to be maximally flat, so this is going to be the Butterworth as defined by the industry. And also the word Butterworth infers a Q of 0.707, again as defined by the industry. And we want this cutoff frequency to be 15 kilohertz. Suppose I want to pass audio frequencies and eliminate, oh, I don't know, tape hiss, or in the digital world, sampling artifacts above 15 kilohertz. If I'm doing a signal to noise ratio, I don't really want to measure noise in and out of the system that I can't hear. So this is actually a useful filter at 15 kilohertz. So the way we begin is we select a value for L and see if it produces a reasonable value for C. So I just let L equal 10 millihenries and then went on to calculate what the value of C would be under those circumstances. So the critical frequency here is 1 over 2 pi square root of LC, standard resonant formula. And then solving for C, we square both sides to get rid of the radical, and then exchange the C for the F0, and working that out, it comes out to be 11.2 nanofarads. So that seems to be a relatively good value, and F sub 0 would be 15 kilohertz squared, and then there's our 10 millihenry sitting in the denominator of that equation. So we've got the parts figured out almost. We've got to figure out what the R is, but that shouldn't be hard. So we want to find the value of R, and the way we'll do that is we'll find the inductive reactance at 15 kilohertz. So that's straightforward, 2 pi FL, and that gives us a value of 942.5 ohms. Now, since the Q is equal to the magnitude of the inductive reactance divided by R, and we know the Q we need, and we have the inductive reactance, all we have to do is solve for R, and it comes out to be 1,335 ohms. So as you can kind of see from this, is that if we divided this 942 by 1335, we'd end up with a number less than 0. I'm sorry, less than 1, and that number less than 1 is 0.707. So that very minor sanity check there kind of makes me feel good about the calculation. So here we have our circuit populated with the values here. So our last step is going to find the poles and the zeros, and the zeros are easy. It's in the numerator here. We don't have an S in here. With a high pass we would. And the 0 would be as F goes to infinity, so this is a non-finite 0. And now what we have to do is to find the poles. So I'm going to be looking at the denominator, and in particular trying to find the roots of the denominator, and those will be our poles. And then our next step, after we figure out what they are, is to go see what they look like in 3 dimensions. So our equation here for the denominator is AS squared plus BS plus C equals 0. So A in this case is going to be equal 1, B is omega 0 over Q, right here, and C is omega 0 squared. So once we have those, it's just a matter of using the quadratic equation to figure out what's going to be happening. So, written the values down here, A, B, and C, and omega squared turns out to be 8.88 e to the 9th power. And omega 0 is kind of important. That's going to be 2 pi times the critical frequency, which is 15 kilohertz. And that comes out to be 94.248 kilo rads per second. So what I'm going to do now is go in and figure out the different components of the quadratic formula. And the reason I'm doing this is I don't want to enter these on a calculator in some big long calculation without being able to check things easily. So I do these sub-calculations here, and actually I do them in Excel, so I can go back and change things very easily. And if I say made a mistake up here, if I change this value, that would propagate through the rest of the spreadsheet and fix everything. Where if I did it by hand in a calculator, well, not so much. I'd have to redo the calculations all over again. So I start out with b squared. I'm going to need that underneath the radical. And then I calculated b squared minus 4ac. Going to need that under the radical. And finally I calculated the square root of that, taking the value, which was negative, because it's over damped, multiplying that by -1 to make it a positive number so I could take the square root of it, and then putting a negative j out here so I don't forget that it is an imaginary number, and that comes out to be negative j 133 E3. So, populating the fields of the quadratic with these values is end up with this guy, and then solving for this, root 1 equals pole 1 ends up being 94,247 at plus 45 degrees rads per second, and the second pole is the second root, and this is just a plus or minus part right here, is also the same magnitude, 94,247, only this is going to be at negative 45 degrees. So remember, when we calculate this part here, is that this is the square root of the sum of the squares, so to speak, and we're going to get the same number under the radical, and then it's up to our plus and minus here to take that into account. So finally, plotting it, I'm going to come out here at 94,247, that'll be the distance, at 45 degrees, and that'll be a pole there. And then for the second pole, because you have to remember these are complex conjugates, this would be the 45 and this would be the negative 45, and since I'm drawing an arrow there, I didn't put the negative down. This will have a magnitude of distance of 94,247 rads per second, and the angle in here is 45 degrees. So I've got my poles all set, and what you can see is that they're not on the real negative axis, negative real axis, so we can expect something that's not all sloping, not a lazy curve, and they're not too near the j omega axis, so we would expect a relatively okay response with regard to a transient. Now what the transient actually looks like, if we were to hit that circuit with a square wave, would look like this. There'd be a little bit of peaking on the positive going and negative going edges of a rectangular pulse, which would produce a little bit of overshoot, as it's called. This is an insertion to the previous video on second order filters, and what I had done back in that video is I expressed the poles in polar form, and many times when you go to plot these, it needs to be in rectangular form. And although we could do the cosine and sine operator on it, actually in the sheet here we have it laid out for us. We just have to look at it and figure out what it means. So what we're going to take a look at for the real poles is the value of b here. And remember that negative b in the quadratic equation sits out in front of the radical. And also we're going to be taking a look at this guy, and this is plus or minus j 133 e to the third rads per second. And basically this is going to be our real and our imaginary part. The only thing we have to do is to take into account this guy right here, 2a. So that's pretty straightforward to do. Let me change pages here so I have a little working room. There we go. So we'll start out with the quadratic equation so everybody's kind of on board with this. The other sheet was kind of busy. And this is what we have here, and the real component is going to be b divided by 2a, and what we know is that a is equal to 1. So very simply, our b is defined as before by negative omega 0 divided by the q factor 0.707, and that leads us to 133 e to the third rads per second. And also under the radical here, we took the square root of a positive number, and then we put a plus or minus j in front of it to indicate that it was truly imaginary. And we have this number here, and as you can probably guess, is that this term needs to be also divided by 2a, but a again is 1. So if we take the real pole, it's negative b over 2, and that simply turns out to be 66.5 kilorads per second. And if we take the imaginary component and divide it by 2, that's plus or minus j again, we can't forget the j, we end up with plus or minus 66.5 kilorads per second. And now to plot this on the negative real axis, we would simply come over for this value, and then for the imaginary components we would be going up and down by the negative j 66.5 kilorads per second, or positive 66.65 K rads per second. Now the reason that the imaginary or the absolute value of the imaginary part is the same as the real is because we chose a Butterworth filter, which has a Q of 0.707. If we had a different Q, these values would not be the same. So don't be misled that it's always going to be the same numbers for the real pole and the imaginary pole. We'll continue. So that completes the design of our filter here. And we'll go up now and take a look at what a second order filter looks like in a three-dimensional plot, and then we'll be able to see how moving these affects the response and how it affects peaking. And other than me saying that it's going to peak as you get closer to J omega, it's not really obvious how that's going to happen. So we'll go take the camera again and stick it in front of a computer and take a look-see at a three-dimensional plot of the S-plane.
This is the response of a second-order filter with complex poles, and these are complex conjugates, so there are two of them. And the real axis, the positive real axis, extends out of the sheet. The negative real axis, negative sigma, extends under the sheet and ends up somewhere over here, and disregard the numbers. And again, what we've done is we've rotated this, and this is the J omega axis right here, and we simply sliced it and took a cut of it. And now we're looking at where that intersected with the actual S-plane, which is kind of like a membrane. We have the two poles here, and those will be the places where the denominator of the polynomial becomes 0. So we get these points of infinities when we end up dividing by zeros. So when cutting this, what we can see is the frequency response of this filter, and this has a Q maybe of, I don't know, 7 or 10. And that cutting would begin at 0, projected up, which would be in the middle of the response curve, and then looking into the second quadrant, the red shape over here traces what the frequency response would be. So again, what we see is a 0 at infinity, which is off the sheet, obviously, infinitely off the sheet, so to speak. And further way of looking at this is, suppose that we had to build a road. What that road would look like on this mountain, if say it had to go directly south to north, no curves, would be the shape of this guy. If we were to move the poles closer to the J omega axis and say that the cutting of the S-plane at J omega would occur up here, is what we would have would be peaks up to here, both sides. And again, we'd only be interested in standing in the first quadrant and looking into the second quadrant where we cut the J omega axis. So a second view of that, a little bit different, would be this guy, and here J omega is clearly labeled. Sigma, the real sigma, is coming out of the page, and the negative sigma, which is not this line, would be projected back into the page. Again, we have two poles, which are complex conjugates, and moving these poles forward would give a higher peaked response. And then in a single order, or a critically damped or underdamped circuit, these poles would swing around and lie on the negative real axis, and that would give us a lazy roll-off. Now, looking at another form of this here, this guy, this is a Bode plot for a first versus second order filter, and in blue here we see a first order filter with a negative 20 dB per decade roll-off, and in red a second order filter with a negative 40 dB per decade roll-off. And remember, in a high-pass world, this would be a roll-up. So for the Butterworth, and this is the S-plane again, we have poles located here, and the angle is going to be 45 degrees, as pointed out in the example. Negative sigma, real axis, positive sigma, and this is the view into the S-plane, and we would be cutting the effects of this pole between the origin here in the J omega axis. So this is the guy that was rotated before when we looked at the actual plot. Now, taking a look at some other circuit variances with regard to Q, this is a circuit with a Q of 0.4, which is said to be underdamped. And what's going to be changing in this is the value of this resistor here. And the lower it becomes, the higher the Q becomes. And what we can see is a relatively lazy second order roll-off, which ultimately would hit negative 40 dB per decade. Looking at the transient response of this, again a square wave, is we can see the effects of the filter by attenuating the high frequency components. This is a roll-off, as referred to before, causes this to kind of be a rounded corner here. Now, thinking about a square wave, it's made up of a fundamental frequency and theoretically an infinite number of odd harmonics. The odd harmonics are higher in frequency, attenuated by the filter. Hence, this is the part of the square wave which is attenuated, would be the edges. Now, this has two real roots. They're on the negative sigma axis. So now we're going to look at a critically damped filter, and that's basically where the absolute value of X at this frequency is equal to R. What we can see is the frequency response looks a little flatter out to the critical frequency. And looking at the transient response, as we see that there's a little bit less rounding in the corners here. So that's a better representation. This particular, since it's a critically damped Q of 0.5, has one real root. And that root would be the quadratic formula. And under the radical would be 0. So we'd have negative B divided by 2A in that instance. Critically damped, and this is overdamped, and this is the Butterworth configuration, maximally flat. The resistance is dropped again. The response is said to be maximally flat out to the cutoff frequency, and that's sitting at about 15K, this line here. And then this would be the negative 3 dB point right there. And looking at the transient response now, well, have kind of effects of underdamped system, is we're picking up little peaks here. And this is the expansion of the peak, and you can kind of see that that's an overshoot. It comes back and settles down. So this isn't too bad compared to Qs that are higher. And that's a key characteristic. When you go for maximally flat frequency response, you have to pay for it somewhere, and that cost would be the way it handles transients. So moving along, we're now looking at a Q of 2, and what we see here is a definite peak out at the resonant frequency. The resistance is dropped again, and now looking at the pulse response, the impulse response, is we see some ringing out here, some peaking, and this would be an expansion here of this point, and what we see is it's going to be oscillating somewhere around the natural frequency of the filter. So it's a shock excited oscillation, and that's because the Q is higher. Q of 5, overdamped. Now we get severe peaking here. And looking at the transient responses, we see a whole lot of ringing. And expanding that here, as we can see that, again, it's kind of like a sinusoid. And it is damped. It's returning to 0 here, so it cannot oscillate. And the roots on this are complex conjugates, as they were on the previous guy. That would be the Butterworth. Where is he? I didn't have that. Won't go back and look for him. So let's take a look at one more, and this is going to be a Q of 10. So the resistance here is down to 94 ohms. We get severe peaking, and notice that we're moving into kind of the response of a series resonant circuit here. Now, as it turns out, the designation, the definition of a series resonant circuit is that it has to have a Q of 10 or higher. Otherwise, it's just a peaked circuit. So the industry says that Q has to be 10 or higher for this to be considered to be a resonant peak. And looking at the transient, well, that's not very pretty. A whole lot of ringing here, a whole lot of peaking, and expanding this out over here is what we see is these ringing sinusoids, which are caused by the tuned circuit of the filter, which would be 15 kilohertz, decreases in amplitude, and the shape of that decrease would bear the equation of e raised to the negative x. So if we were to build this, say, and this is the only part we'd be interested in, it would be the product of a sine wave times an exponential raised to a negative quantity. So this also is underdamped, and we have complex conjugate roots again. And notice the angle here, it's 87 degrees, and it's not far away from the J omega plane. Now, we can't actually be on a J omega plane with an LC filter, again, because there's no external power source. And the only energy going into it is the signal, so it can never really oscillate. But what you do see here is some severe ringing, so that probably wouldn't be good for much of anything that has transients in it. So that'll conclude, and thank you for watching.